Welcome. This is a universally compliant, more environmentally friendly and rigless tubing compaction project presentation. Made possible by the Oil and Gas Technology Center, Oil and Gas Innovation Center, the University of Glasgow, and Oilfield Innovations. This is a third in a series of videos explaining the Oil and Gas Technology Center and Oil and Gas Innovation Center validation projects for tubing compaction. First, let's talk about the Oil and Gas Technology Center Real-Scale Compaction Project. This involved using 9 5/8 inch casing and compacting 4.5 and 5.5 inch tubing within the casing. The setup is shown here. The casing was laid out upon the ground as you see. Surface plasma cutting was used to simulate downhole cutting, whereby a cut piece of split tubing was placed into the casing, followed by unsplit tubing, and a piston arrangement. A triplex pump was used to drive the piston to compact the tubing with fluid. Through this simulated wellhead with a swedge at the upper end, Chicksons, and a high-pressure hose to pump fluid into the casing. We couldn't find a donor and we couldn't afford an inflatable packer for the trials, so we used a long cylinder and cement wiper plugs to simulate a downhole inflatable packer, which can be used as a compaction piston. As you'll see over the next few minutes, we performed quite a few tubing compaction trials. Here we vertically sliced the tubing into quarter sections and compacted it. As you can see, the 4.5 tubing which is being compacted bends very easily when sliced into quarter sections and rolls and folds into very tight compaction configurations. Generally, when sliced into quarter sections, the tubing will roll and fold into tightly compacted nests. But sometimes a compaction spear will be able to get side by side with the quarter sections. Compacting tubing actually sliced into quarter sections creates compactions with a high degree of friction, and many times is difficult to pump them from the simulated casing strain. A high level of friction is not necessarily a bad thing if it's placed at the bottom of a compaction so that it supports the tubing above it and the cement plugs placed above the compaction piston. To find the limitations of tubing compaction, we tested a lot of different configurations until we finally came upon the right configuration, which allowed us to compact tubing using a low frictional arrangement that also had relatively low compaction pressures at the pump. An optimal tubing compaction configuration severs the tubing just below the couplings, so that when you compact the spear, and the spearhead being the coupling, it progresses all the way down to the target pin, which is shown here as a 50% compaction by putting the box next to the pin. An optimal compaction configuration also splits the target tubing twice and leaves the spear whole, so that it may progress between the half-split target tubing, or alternatively swallow half of the target tubing. Our compaction trials found very little difference between 4.5 and 5.5 inch tubing within 9 5/8 inch casing. And generally speaking, when you slice the tubing in this optimal arrangement so that you have a coupling for a spearhead and two halves for a target, once you shear through any initial resistance, the spear tends to find the split between the target tubing, and the frictional values go way down along with the pump pressures. After numerous compactions of 13 chrome L80 5.5 17 pound per foot and 4.5 inch 12.6 pound per foot L80 13 chrome tubing within 110 psi 9 5/8 inch casing, we found that the results are repeatable and similar regardless of whether it's 5.5 or 4.5, and regardless of whether the spear swallows the target tubing or the target tubing swallows the spear, or the spear compacts alongside the target tubing. Once the compaction spear passes through the initial resistance of finding the split in the target tubing, the frictional values and associated pump pressures are relatively low. We also found that this optimal tubing compaction configuration is versatile enough that you can split the tubing once and use the compaction spear to swallow the tubing by following the one axial split on one side and using the coupling to shear the target tubing wall on the other side. We were even surprised by this type of compaction, whereby this example shows the target tubing sliced once and the spear joint shearing the opposite side of the target tubing to swallow half of the target tubing. The Oil and Gas Innovation Center part of the project worked with the University of Glasgow to validate the tubing compaction process and create a mathematical model, which is shown here. Explaining a material mechanics finite element model is beyond the scope of this video, but the University of Glasgow has validated that tubing compaction is viable. They've also created a model for predictive purposes. Regarding prediction, this is an actual pump pressure graph for the compaction you see on the right. The maximum pressure was 4,340 psi when the spear was trying to find the split in the target tubing, after which the pressure dropped to approximately 500 psi when the spear was traversing within the two halves of the target tubing. Upon finding the end of the split in the target tubing, the pressure began to increase, and we stopped the simulation so that we wouldn't damage the seals on our cement wiper plug. That completes this part of the validation process, and you can continue watching the fourth part of this video series about keeping risks as low as reasonably practicable by finding the next installment on YouTube. Thank you for watching.